Hello, everybody. Welcome. Hello. We're going to get started in just a couple minutes. Let people continue to stroll in. And for those of you that missed the first session last week, really welcome. It's your first time joining us in this course. We're so excited to have you. Great. Hello. I love when there's an active chat. It makes it so fun.
Makes me happy.
Ooh, Chicago. Where's everybody else tuning in from? I'm in Brooklyn. Olympia, cool. Seattle, Oregon.
So many places.
Cool. Oh my gosh, so many places.
Yeah.
Welcome.
Someone is very excited about being from Vermont, which makes sense. Vermont's beautiful.
All caps. Boston, nice. I grew up outside of Boston. Connecticut. Lots of snow. I can't think about snow yet.
No, I'm not ready. I'm not prepared. My winter jacket is still deep in the back of the closet.
Exactly. Oh, wow. All right. Well, I am going to kick things off, especially for those that weren't with us in the first session last week. Hello, welcome. You have joined us for the second session of Moya's course, Facts-Based Fictional World Building. My name is Kiki. I'm with Atlas Obscura on the Experiences team. And I'm going to be the moderator for this course today. If you have any technical issues, feel free to shoot me a note through the chat, and I'll be able to help you out with those. Again, for anybody that's joining us new this week, a little bit about Atlas Obscura if you are also new to the company. Our mission is to inspire wonder and curiosity about the incredible world that we all share. And now more than ever, there's a need to stay connected, not only to a sense of wonder about the world around us, but also to each other. So again, we want to thank you so much for joining us as we continue to explore ways to transition our real-time experiential content into the virtual world. If you haven't already, we encourage you to follow and share the hashtag AOExperiences. And to check out atlasobscura.com for more online courses and shows, our atlas of amazing places, and our unique stories, trips, and videos. Few housekeeping notes before we get started with the second session tonight. You'll be using Zoom for the entirety of this course. So that link that you've clicked on to join us tonight will be the same link that's going to be for each session throughout the course, which there are 8 for this course. We typically encourage everyone to use speaker view as the best way to view a course. Moya will be sharing her screen throughout the majority, if not all of tonight. So that default should be there for you as viewing her slides. And then you can also see some folks in the gallery if you change your view in the top right to be speaker or gallery there. As a reminder, all of our sessions are recorded, and they're recorded in speaker view. And since most of you will not be speaking, you won't be in the video, but if for any reason that makes you uncomfortable, feel free to turn off your video in the bottom left screen of your Zoom. If you have questions or comments throughout the course, this chat is already very lively, so keep that going. Throw in your questions, your thoughts, keep the discussion going. And as you're doing that, please remember to be cool. We don't anticipate anyone being disrespectful in a space like this, but please do note that if anyone's being disruptive or disrespectful in any way, we might remove you without warning. Lastly, especially for those folks that are just joining us for the first time tonight, I'm about to drop 2 links in the chat. The first is the Google Classroom, which we encourage you to join if you haven't already. In there, there's a really cool feature called the stream. That's going to be kind of your default view in Google Classroom. And Moya will be able to drop in discussion points, and you can comment or add other points for discussion throughout that stream in the Google Classroom. So it's a great way to stay in touch with your classmates outside of sessions. The second document that I'm going to put in there is a Google Sheet that if you so choose, you can put in your name and contact information if you want to stay in touch directly with any of your classmates outside of these sessions and after the course ends. Moya and I were talking about right before this, we envision people, when it's okay to go to a coffee shop, meeting up again and building fictional worlds together after this course, and that doc is the best place where you'll be able to do that. I think that is everything that I need to cover. So I'm going to hand it over to Moya now. Sorry about the sirens, and you can take it away.
Great. Hello, everyone. Welcome back to the second week of world building. Like I promised, I'm going to start by lighting this candle behind me so that we know it is world building class time. And I know you can't smell it through the screen, but it does smell delicious and it makes me happy. So today we're going to be talking about building the stellar system. This is the astronomy lecture of the course. I'm so excited to talk about it with you, but it is going to be very information dense. I like to think of this part of the course as, oh yeah, I'm glad the sound is better. I like to think of this part of the course as me giving you like individual Lego pieces that you can use to build your world later. And those individual Lego pieces are tiny little bits of information that you can mix and match and manipulate at your will. While I'm going through this talk, if you hear a piece of information that you think that reminds you of a story or a book that you've read, for example, I am going to be talking about moons because there are moons in space, and moons remind me of the Broken Earth trilogy by N.K. Jemisin. I have the second book here. So if what I say reminds you of a book or story, write it in the chat so that other people can collect examples of books that are relevant to the course. All right, let's start with an icebreaker just to get us going and thinking about world building, like literally building worlds, building planets. So write in the chat what you think makes Earth habitable. What is it about Earth that makes it good for life? Amy was the first to say water. Well done, Amy. Oxygen, atmosphere, location. I see Dan said location. What do you mean about that? Do you mean location within the solar system, location within the galaxy? Distance from the sun, yeah, so location in the solar system. I see people talking about temperature, magnetic fields, complex chemicals. Yeah, there are so many different things that make Earth habitable, and that might feel overwhelming, but the beautiful thing about that is that it means, you know, we don't need all of those things for life to happen. We just need a critical mass, a critical subset of those things for life to happen, especially if you aren't limiting yourself to life that looks like us. If you're willing to build a story or build a world inhabited by totally different types of creatures, then you have even more freedom in what you make your world look like. I'm going to go through some definitions in case I end up using some terms that you might not be familiar with. So we hopefully have all heard the term solar system, and solar system specifically refers to our solar system. It's the system around the sun, which in Latin is Sol. But if you want to generalize to other stars that have planets around them, then that's a stellar system. So it's a collection of planets, comets, and asteroids, and dust, all of the stuff that makes up a solar system or a stellar system, and it's gravitationally bound to at least one star. We're going to talk about how you can have multiple stars in a system in a little bit. These are some examples of solar and stellar systems. So the one on the left is our solar system. You can see the sun all the way on the left, followed by the 8 planets in our system. This is not to scale, because if you want to put the solar system on a picture to scale, it's impossible if you want to do it in terms of both distance and size of the objects, because space is really big. And that's one thing that I really want you to take away from this lecture. Space is really big. Things are far apart. Light is the fastest thing in the universe. Our sun is 93 million miles away from us, and it still takes light 8 minutes to get from the sun to us. and the closest star to us is 4 light years away. So think about that. Like, really take a moment to sit with how big the universe is if the nearest star to us in our dinky little suburb of the Milky Way galaxy is 4 light years away. And that means that there's just a lot of space for you to work with, pun intended. The characteristic, oh, I didn't even talk about the system on the right. The system on the right is called the TRAPPIST-1 system. It has 7 planets in them, and 4 of them are within the habitable zone of this system, or we think they're within the habitable zone of their system. Yeah, TRAPPIST is awesome. Most of them are around the same size as Earth, but the system's tiny. The entire system, the entire TRAPPIST-1 system could fit within the orbit of Mercury in our own solar system. It orbits a star that's a lot less massive than our sun, so it's a lot smaller, and that means everything is just more compact. The characteristics of all of these different planets and the way that they interact with other planets and the way that they interact with their star, those characteristics affect the planet's environment. And now I'm gonna tell you how it does that. I like to think of this in terms of dials to adjust. So if you turn the dial one way, how will that affect environment on the planet? So here are my different dials. There are a lot of them. There are a lot of different factors that you can keep in your mind, a lot of different factors that you can manipulate when you're building a planet or a stellar system from scratch. And there are a lot of them. I know it might be a little overwhelming. I'm not going to talk about each one of these individually. I will talk about most of them. There's one that a lot of people brought up in the question on Google Classrooms about planetary neighbors. And I don't have a slide for planetary neighbors, but I will say that there are a lot of cool things you can do with planets that are close together. So thinking back to the TRAPPIST-1 system, all of the planets are really close together. And that leads to interesting things like, if life does form on one of the planets, it's a lot more likely that life will form on the others, because stuff in space doesn't sit still, it moves. Tiny little microbes can attach themselves to a rock on one of the planets and then travel to one of the other planets. Having close planetary neighbors also means maybe it's easier for a species on one of the planets to develop astronomy and to travel to another planet because it's so much closer. It takes months, 6 months, I think, to get to Mars. Or 3 months. It takes months to get to Mars. But if your planets were a lot closer together, then those missions wouldn't be as difficult to pull off. So that's just a few thoughts on planetary neighbors. Now let's get into the other dials. The first dial is the first one you have to think about when you're building a stellar system from scratch. You have to start with the star. So let's talk about the different types of stars that there are. This link will take you to an article that goes through the differences between stellar classifications. So the most important thing to know about a star is always its mass. As an astronomer, I can look, maybe not me, because I don't study stars, but like an astronomer who does study stars can look at the mass of a star and determine exactly to within like a tenth of a percent in error when that star is going to die, and we can really accurately figure out how it's going to die. So this graph has a lot of information on it. On the bottom x-axis, it tells you the mass of the star, with the most massive stars being on the left. And you can see that the most massive stars live the shortest amount of time. You can almost think of stars as musicians. The stars that are really massive, they burn bright and they burn hard, and they live short lives. The curse of the 27th year, it really applies to stars. So the age of a star, or the life expectancy of a star, is here on this y-axis. And across the top, I'm giving you the name of the type of star. Astronomers have classified stars with letters. So there are O-type stars and B-type stars, all the way down to M-type stars, which are the least massive. Also, if you have any questions about this at all, put them in the chat. I'll try to get to them, but if I miss them, then we can come back to it at the end of the lecture. A smaller star means longer time for habitable planet to exist. Yes, exactly. So the least massive stars, the M-type stars, they live for 100 billion to trillions of years. In fact, these M-type stars live so long that we've never seen one die because the universe is only about 14 billion years old. So we don't know what it looks like when these stars die. What's our star type? I'm going to get to that in just a second. So the stellar type, the type of star that you orbit, affects different things on the planet, like how long the system is going to survive. So Ashley beat me to it. Good job. It also affects the temperature of a planet. If you have a hotter star, it's going to be emitting more energy, more heat, more radiation, and that's going to translate to having a hotter planet. Oh, I should also tell you that like the unit of mass is in solar masses. Yeah, so Slater is quick on the draw. Here on the right side of the graph, I'm showing you the average temperature of these different stellar types, and the most massive stars are the hottest, and the least massive stars are the coolest. So where it crosses, just coincidentally, is where the sun is, right there as a G-type star. This doesn't mean that our sun is special in any way because it happens to be where those two lines intersect. It's just a coincidence. Solar mass relative to our star. Yeah, so one solar mass is the mass of our sun, which I don't know in pounds, but one solar mass. This is typically how astronomers use units. We put it in terms of things that we know in our own solar system. So we say things like one solar mass, one Earth radius, one Jupiter mass, or something like that. The type of star you have also affects the amount of radiation that you get. I don't have anything here about the electromagnetic spectrum, but different stars have different spectra. A spectrum is a graph that shows you how much energy a star, or anything really, is emitting at different wavelengths of light. And the cool thing about different stellar spectra is that it actually influences things that aren't super obvious. For example, we see in a very, very tiny range of the electromagnetic spectrum. We call it the visible range of light. Smaller stars are dimmer and cooler. I'm sorry if I mixed that up before. Yeah, so smaller stars are dim and cool. Big stars are bright and hot, and they live short lives. Yeah, thanks, Evan, for asking me to clarify. What was I talking about? Oh, right. So we see in the visual range of the electromagnetic spectrum, and that's because that's where our sun emits the most energy. So if you look at the sun spectrum, it actually is this curve that peaks right at green wavelengths of light. So that's what humans can see best. If you lived around an M-type star, for example, most of the energy for M-type stars is in the infrared part of the electromagnetic spectrum. So maybe people on those planets would see in the infrared, which, if you've ever used an infrared camera or an infrared sensor, it senses heat. So it just shows a very different view of the world if you can see in different wavelengths of light. Another thing to remember is that most stars aren't born alone. They can be born in pairs. So you can have a binary system. They can be born as triplets. So you have a triple system. I think the most stars we've ever seen in one system is 7, which is a lot of stars. Having more than one star does complicate the orbits of the planets in the system. You can do it in a lot of different ways. You can have planets, you can have the stars close together in the center of the system, and then the planets orbit around all of the stars at once. Yeah, like the 3-body problem. You can have planets that weave in between the stars. You can have so many different complicated kinds of orbits. So you can feel free to just like do whatever makes sense for your story, because basically anything is possible, except going like through the star in a tunnel. Stars aren't donuts. You can't just like tunnel through. And some stars do weird things. So stars flare, they send out these big shocks of radiation and charged particles. Flares are related to things like the aurora here on Earth, where those particles from the sun actually interact with our planet's magnetic field. So you can use that to maybe make some beautiful aurora on a planet. They also have star spots, and some stars pulse in brightness. So they get brighter and dimmer. They actually sometimes get bigger and smaller over time. And this link will take you to an article that explains how that works and what conditions you need to make that happen. It's not quite twinkling. So twinkling is what you see when light from stars passes through our atmosphere. It actually gets messed up in some way. We call it aberrations. And the pulsing of stars is actually inherent to the stars. So the star itself is changing in size and brightness, and it's not just an effect of the light passing through the atmosphere. On to stuff about the physical planet, its size, its mass, and what it's made of. This chart is from a paper that my advisor and one of his other graduate students published a few years ago. It shows the relationship between the mass of a planet and the radius of a planet. And it's not just like a straight line. So you can separate it into chunks. So for example, Terran type worlds, worlds that are like our sun probably wasn't born alone. We think that it had a twin, but it was really far away from us. So it, through gravitational interactions, got pulled away even further from our system. It's called Nemesis. So you can look up the star Nemesis if you want. So Terran worlds over here on the left are worlds like the Earth, Terra meaning Earth. And that's probably what most people think of when they want a world build. I imagine most of you will probably be focusing on rocky planets, planets like the Earth. But you can see how different types of planets, how their masses relate to their radii. Smaller planets are rocky, and a study came out in 2014 or 2013 that found that most planets bigger than 1.5 Earth radii, or 1.5 times the radius of Earth, are gaseous. So if you want to have a rocky planet, it really can't be bigger than 1.5 times the size of Earth. These rocky planets are made out of elements, heavy elements like iron and nickel, mostly, like that's what their cores are made out of. And that rotating liquid metal core is what provides a magnetic field, which can protect us from strong radiation from the sun. It gives us beautiful things like aurora. It's how birds navigate. It's how humans navigated once we figured out how to make compasses and how to use things like lodestones. But we talk about navigation in next week's lecture. Bigger planets, on the other hand, are mostly gaseous. So if you think about the big planets in our solar system, things like Saturn and Jupiter, those are really big. They're mostly made out of lighter gaseous elements like hydrogen and helium, although the gas planets still have solid cores, but they're not made of, or usually they aren't made of things like nickel and iron, because the heavy elements usually are closer to the star in a stellar system. But the cool thing about really big gas giants like Jupiter is that the pressure and the density closer to the core of the planet is so intense that you end up with things like metallic hydrogen. Hydrogen isn't a metal. Astronomers who call everything heavier than helium a metal, we know that hydrogen isn't a metal, but the conditions on Jupiter are so intense that you can actually get metallic hydrogen that acts as a solid and interacts with other things around it in really interesting ways. So that's something you might want to use for a story maybe. We think, but we're not sure, this is an active area of research. We think that rocky planets mostly form close to their stars. If you look at our solar system, all of the inner planets, Mercury, Venus, Earth, and Mars, are rocky. But if you look at the outer planets, that form further away from their stars, they're gaseous. And that has to do with what elements are present in different parts of the solar system when planets are still forming. But a general rule of thumb is planets close to the star are rocky, planets far away are gaseous. You can't fly through a gas planet. Yeah, you can't fly like through the middle, but you can definitely take like a long journey around through its atmosphere. And if you take the size and mass of a planet and you combine them, then you can get the density and the gravity on the planet. So here on Earth, I'm going to ask you to think back to your high school physics classes. What is the acceleration due to gravity here on Earth? Does anyone know? Yeah, some of you are getting like precise, 9.8 meters per second squared. Yeah, so meters per second squared, that's a unit for acceleration. So when you're standing on Earth, the Earth's gravity is pulling you down at a rate of about 10 meters per second squared. If we lived on a much more massive planet, then that force of gravity would be stronger. If we lived on a planet that had the same mass, but it was bigger, if it had a bigger radius, then when you're standing at the surface, you'd be farther away from the center of the planet. So you would actually experience weaker gravity, because gravity gets weaker as you move away from the central point of whatever is exerting gravity on you. Yeah. Now on to planet obliquity and moons. Obliquity might be a term you've never heard before. I definitely had never heard this word before I became an astronomer, but obliquity is the tilt of a planet. You may have heard that the Earth is tilted on its axis, so we're not pointing straight up and down. Write in the chat if you know what angle Earth is tilted at. But this obliquity or this tilt determines the seasons on a planet, but that's barring any internal mechanisms like volcanism. Yeah, 23 degrees. Yeah, so we are about 23 degrees from straight up and down. If you have internal mechanisms, that's going to mess with your seasons shifting. That's totally the wrong thing to hit. An obliquity, I'm just going to tell you the extremes. So an obliquity of 0, if you have absolutely no tilt, it means that you don't have any seasonal shift over a year on most parts of the planet. So if you have a tilt of 0, imagine my fist is the sun and my finger is the axis of the planet. Hopefully you can see it well enough. As the planet goes around, it continues to point in the same direction, and the planet's rotating like this. So places along the equator, they're not getting any seasonal shifts right now. But places at the poles, over here, it's summer. It's summer for this pole right now. But as the planet orbits the star, over here, it's winter because it's far away from the star. So you do get seasonal shifts at the poles of the planet, but like it requires some complicated thinking, but seasons are difficult on a planet with 0 obliquity. On the other extreme, an obliquity of 90 degrees. So if you're, I was totally wrong before. What I just did, that was for an obliquity of 90 degrees. So you have extreme seasonal shifts. An obliquity of 0 means truly that there are no seasonal shifts here. Because as you orbit around, you just are going from day to night, and nothing is changing. Seasons are determined by how much direct sunlight a place on the planet gets. That's what determines a season. I'm taking way too long. I'm gonna speed this up. I'm sorry. Moons do really cool things. So they can stabilize a planet's tilt, but they can also mess with a planet's tilt. A few of you asked in the Google Classroom, what happens if I have multiple moons? Well, if you have multiple moons, then their gravity can fight with each other, and it can actually move the planet around. So you end up with a tilt that changes over time. So that means that the seasons will change over time. Our tilt is also changing a very little bit. It's called precession, where the axis of Earth does point at different stars over time. So right now, our North Star is Polaris, but in 20,000 years, our North Star will be Vega. So we are moving, but it's only a tiny little bit. Moons also affect tides if you have oceans. They can provide reflected light at night. If you have a shiny moon, then it will reflect a lot more light from the sun. If you have multiple moons, then you're just getting a lot of light shining onto the night side of the planet. And planets or moons can protect planets because some moons have their own magnetic fields. I read a cool article lately, like earlier this week, about, it's only Tuesday. So over the weekend, I read this cool article about how we think the moon, our moon, had a small magnetic field early on in the solar system's history that interacted with Earth's magnetic field, because we see particles on the moon that really should have only come from Earth and been like transported over magnetic field lines. And the moon's magnetic field can protect other planets if they don't have a strong enough magnetic field. Rotation period. Lots of questions. Could tides be affected by a closer planetary neighbor? Yeah. Anything with gravity can affect tides. So anything with mass has gravity. On a planet that, most planets are rotating, most things in space are rotating or spinning, even black holes are spinning. But if you have a planet that's spinning really quickly, then the centrifugal force, this imaginary force that pushes things towards the outside of a spinning object, it can actually make the planet bulge more at the equator. So instead of being a circle, it ends up looking oblate, like a hamburger that you squash down because you were super excited to fit it all in your mouth. But our planet does that a little bit too. From our rotation, it is slightly oblate. Some planets are tidally locked, meaning that one side of the planet is always facing their star. You can see that in the little image here. On those planets, one day, so one rotation on the planet is exactly the same length as 1 year on the planet, the amount of time it takes the planet to go around its star. Our moon is tidally locked to us, which is really cool. And these tidally locked planets, they have a day side and a night side. And in between, they have this awesome terminator zone or a twilight zone where temperature is good because the day side is really hot and the night side is really cold. But in this terminator zone, you end up with super intense storms because there's a lot of wind going from the hot side to the cold side and back and forth. A tidally locked planet equals red dwarf star. So a tidally locked planet can happen around any type of star. It doesn't have to be a red dwarf. No. Rotation speed of a planet does affect its weather. If you've heard of the Coriolis effect, which is as the Earth rotates, because the equator is rotating faster than the poles, then wind going from the North to South Pole actually gets twisted along with the rotation of the planet. If you have a very fast rotating planet, then that twisting happens even faster. It's more extreme. So you get more extreme storms like hurricanes. A slow rotating planet, on the other hand, can give you longer exposures to sunlight because it takes more time for a part of the planet to move from under the sun. And if you have more or longer exposures to sunlight, then you get more clouds because water is evaporating, and you can have hotter surfaces. There are really cool things you can do with the rotation of a planet. Rotation also affects perception of time. I saw some people asking about that in the Google Classroom. If you have a fast rotating planet, then days are really short. If you have a slow rotating planet, like Venus, for example, in our solar system, 1 day on Venus is about 120 Earth days. So that will affect your perception of time. Maybe you even have to come up with totally different ways to track time if it doesn't align with your biological cycles. We have a circadian rhythm that's about 24 hours long. So it makes sense for us to keep track of time by the motion of the sun. Although maybe we have that circadian rhythm because that's what our planet's rotation is. But you can come up with really creative ways to measure time on different planets. Thanks for listening to ExoLore, Harry. Does Narnia spin faster then? Does time move faster in Narnia? Is that a thing? Oh, cool. Maybe. All of those folklore tropes, especially in like fairy stories, where you see a lot of examples of people going into the fairy realm, and then they come out and all of their family members are dead, and it's been like 200 years. Yeah, you can definitely create a scenario, especially if you want to deal with fantasy, where it's just another world that rotates more quickly or has a different way of time passing. Tidally locked worlds can still be habitable. I mean, we find Earth even in the most extreme conditions here. There are things that live in volcanoes. There are things that live at the deepest parts of the ocean. So one thing I'm going to tell you now is I don't think there is any type of planet that you can create that absolutely would not have life on it. I do think there are lots of types of planets you can create that probably wouldn't have human-like Earth on it. But if you don't want to deal with humans and you just want to come up with a wacky type of planet, like go for it. You can figure out a type of life that fits there. And we'll talk about that in the biology lecture. Albedo is another one of these dials. It's how reflective a surface is. And different types of materials have different albedos. A high albedo means it's really reflective or shiny, and a low albedo means it absorbs most light. So snow is really reflective. If you've ever, who here said it just snowed, right? If you went outside, assuming if it's still light wherever you are, if you went outside, the snow would be really shiny. That's why skiers wear really dark goggles so that the light reflected off of the snow doesn't hurt their eyes. So snow is really shiny, and then it goes down until you get to the ocean, which is kind of surprisingly not that reflective. So it's a good thing that we have a lot of our planet's surface is covered in ocean, because it does help reflect a lot of light and therefore heat back into the upper atmosphere. On planets that have high albedo, more sunlight gets reflected back into the atmosphere, and even small changes in albedo can cause environmental and climate shifts. So maybe you've heard of LA painting their streets white. It's because black streets, black concrete, absorbs more light and heat. So LA was getting really, really hot because of all of its black streets. But if you paint the streets white, they're more reflective, so you're not absorbing as much of the heat. And that's just one city on Earth, but if you think about it in terms of the entire planetary system, then you can have really extreme effects. Shiny moons, reflective moons with high albedo are easier to see, and planets that are more reflective are easier to see too. And this can influence things like, when do life forms on your planet even start to realize that astronomy is a thing? When do they start to realize that there are other planets out there? Because if you can't see the other planets, you're not going to know they're there until you develop the type of technology to see things that you can't see with your unaided eye. So you want shiny planetary neighbors if you want your life forms to develop astronomy early on. Now for stuff about the planet's orbit. The orbital radius is also called the semi-major axis, and it's related to the period of a planet. And the period is the length of a year. This is Kepler's third law, if you want to look up the actual equation. But if you are just looking for a relationship, then the period squared is proportional to the radius, or the semi-major axis, cubed. So as you increase your period, then as you increase the distance that a planet is from its star, it also will increase its period in like a very mathematically defined way. Eccentricity is how round your planet's orbit is. Less round means, so if you have a very oval-shaped orbit, then you're going to experience these big temperature swings. So when your planet is closest to its star, it's going to be really hot. And when your planet's far away from the star, it's going to be a lot cooler. And maybe those extreme temperatures are totally fine, but a big temperature swing is harder for life to handle. So think about that. If you want to have a really eccentric planet, then you're going to have to figure out what type of life forms can handle that big extreme temperature swing. A planet's eccentricity can change over time from interactions with other bodies that exert gravitational force, like planetary neighbors or lots of moons. Actually, probably not moons, because moons are orbiting planets. So like they're not going to take the planet away from its orbital path. So other planets. And planets move faster when they're closer to their stars, which is awesome. This is another of Kepler's laws. Is it his first or his second? I don't remember. It's another one of Kepler's laws. So when planets are close to their stars, they move really fast. So in this scenario, in this image on the screen, the blue planet would have a very short summer. And then they spend more time further away from their star because they're moving more slowly. So it would have a very long winter. Is that it? Okay. And place in the galaxy, this is one of my favorites because my thesis research is about galactic habitability, trying to find a place in the galaxy where habitable planets are most likely to form. So your place in the galaxy affects things like, can you see stars? So there are some parts of the galaxy that are a lot dustier than our part of the galaxy. And if you're in the middle of a big dust cloud and you happen to orbit a star like our sun, so you can only see in the visual range of the electromagnetic spectrum, then you wouldn't be able to see through all that dust. But if you are in a dusty part of the galaxy and you orbit a star like an M dwarf, which has more of its energy in the infrared part of the electromagnetic spectrum, your life forms on that planet might see in the infrared and they could totally see the dust. They could totally see all the stuff around them. So your place in the galaxy can interact with the type of star you have to determine what people see when they look out at their night sky. If they can see, because not all life forms can see, and that's fine. Is your world near a star that explodes in a supernova? That's pretty dangerous. They emit a lot of dangerous high energy radiation. And there are, to my knowledge, there's not a place in the galaxy where supernovae explosions, where supernovae are a lot more common, maybe in the spiral arms. So if you look at this picture, you see those beautifully drawn out, like the characteristic spiral arms of the Milky Way galaxy. There are just more stars in the spiral arms, so you will probably find more supernova explosions there. Are metals more likely in certain locations? Yes, absolutely. You find more metals closer to the center of the galaxy, and then it kind of tapers off as you move further out in the disk. And when you get to the halo, this link at the top will take you to an article about the anatomy of the Milky Way galaxy. So it'll tell you about what the different parts of the Milky Way are. The halo is this big bubble of mostly dark matter and a few globular clusters of stars. The metallicity, the amount of metals that you find is really low in the halo. Close stellar encounters. This is my original research. I'm really excited to tell you about it. Close stellar encounters are much more common in the center of the Milky Way galaxy, the part of the galaxy called the bulge, because stars there aren't moving on slow, predictable circular orbits around the center of the galaxy. Stars in the bulge are moving a lot faster. They're a lot closer together. There are 10 billion stars kind of, what's the word? Just like clumped together in this tiny part, relatively tiny part of the galaxy, and they aren't moving on circular orbits. Some of them are moving on these weird rosette shapes. So if you ever played with a spirograph, for example, that type of shape is actually how stars move in the center of the galaxy. Some of them are X-shaped or boxes almost. So about 80% of the stars in the Milky Way bulge have close stellar encounters that can, some of them, if the encounter is close enough and the stars involved have the right, pairing of masses, it can actually rip planets away from their stars. If you want to build a world that isn't in the Milky Way at all, which I would love to see, then there are some things you have to think about. So there are different types of galaxies. There's spiral galaxies like the Milky Way, but there are also elliptical galaxies. Some galaxies collide with each other. In about 5 billion years, the Milky Way is going to collide with Andromeda. So maybe you don't even have to put your story in another galaxy, but you just have to put it in the Milky Way 5 billion years in the future. When galaxies collide, not much happens. Stars are so far apart in galaxies that they won't actually collide with each other, but all of the gas will collide with each other. And when you get gas swirling together, you get new stars. So if you are in a situation where two galaxies are colliding, it would actually make the night sky a lot brighter. So like depending on where you are in those galaxies, it might look like daytime during the night. Elliptical galaxies are often older. You may hear an astronomer refer to them as red and dead galaxies. Older stars mean that you can have older civilizations, which means they can have more time to propagate throughout their galaxy. So maybe if you want to put something in an elliptical galaxy, that might make it more likely to have like a galaxy-wide, centralized, intelligent species that's just taken over the entire galaxy. That would be really cool to see. And it's more likely, I think, in an elliptical galaxy than a spiral galaxy. Some stuff that I saw you asking in the Google Classroom that didn't make it onto any of those other slides. A lot of you wanted to know about different events that are related to folklore, which is awesome. I totally get it. And there's some cool stuff. So some examples of events in space that make it into folklore are eclipses. We have so many different myths about what causes eclipses. Things like there are a lot of cultures from around the world that explain eclipses by thinking that some big powerful being is eating the sun. Like that's how they explain solar eclipses. And that leads to really cool rituals. Like I don't remember where, but there is some group of people who used to have a ritual when they knew eclipses were about to happen. They would go outside and they would make a lot of noise by like banging pots and pans to try and scare away the creature that was about to eat the sun. So that's one way that space influences folklore. Comets, meteor showers, asteroid impacts, those all affect folklore in different ways. One person asked, how common are meteors and meteorites and asteroids? Very common. Earth gets hit by small rocks every single day. In fact, every year, the Earth gets 12 billion kilograms heavier from space rocks and space dust falling on the planet. And supernova explosions. We've seen evidence of people thousands of years ago recording supernovae that they see because they create these really bright bursts. So it almost looks like a new star just appears out of nowhere in the sky. And people take note of that and write stories around them. I think I saw someone earlier in the chat asking about a torus-shaped planet. And someone on Google Classrooms asked about a flat planet. Objects in space usually are spherical, especially small-ish objects like planets. So they're usually spherical. Even galaxies are typically spherical unless they get big enough and they're spinning fast enough, and that's how you get a circular disk like we see in the Milky Way. But you don't have to build a world that's a physical world. If any of you have ever seen The Magicians, there's that scene where Umber, I don't remember. He creates Cuba, the tiny little cube world, or Orion in Men in Black, where he has the collar that has an entire universe on it. You don't have to build a world that's a literal physical world. So you can imagine like a very powerful being in the real world creates a simulation or creates a tiny little pocket world. And that can be flat, that's totally fine. Some planets don't orbit stars at all. They're called rogue planets, and they're actually really common. Astronomers think that there are on the order of 100 billion rogue planets just floating around in the Milky Way galaxy, not orbiting any stars, and we can't see them because they're dark, but they're there, which is really cool. And sometimes they happen because of those close stellar encounters, ripping planets away from their host stars. Some people asked about black holes. This article will take you to a page that just like explains some stuff about black holes, but one big misconception that I wanted to clear up right away is that there's not just one black hole in the Milky Way, there are 10 million black holes in the Milky Way. And most of them are what we call stellar mass black holes. So they're really small. They're only the mass of like a few solar masses, as opposed to Sagittarius A star, which is the supermassive black hole in the center of our galaxy that's 40 million solar masses. So that's the biggest one. That's like the big Mac Daddy black hole. And then there are 10 million other smaller black holes throughout the galaxy. And you can imagine a world that interacts with one of those smaller black holes. Orbits can change over time, and this is planetary orbits. So planets can migrate through the system. If you want to learn more about that, I recommend looking up hot Jupiters. And the moon is moving away from us every year. It's getting about 1.5 inches further away from us every single year. So things move. If you you can imagine a story where the main conflict is based on something in space changing. And I think that'd be really cool because most people think of space as a very static thing. Once space is set up, it doesn't change, but that's so far from the truth. Space is changing all the time. Even stuff in our tiny little podunk solar system is changing all the time. Some things to think about as you're building your world. I'm just gonna put all of these up here. If you're building your world and you wanna start with the astronomy part of it, which I do recommend, especially if you're building a world from scratch, then just think about these things as you're going through. And now let's build a world, right? That's what we're gonna do at the end of every class. So if you want to build a world from scratch, this is what I'm going to do throughout the course because it's my favorite way of building worlds. So if you want to build a world from scratch, then start at the very beginning. Julie Andrews is a very wise woman. Start at the very beginning. And when it comes to a stellar system, the very beginning is the formation of the star, and which leads to the rest of the stellar system. So answer questions like, where in the galaxy is the star? Do you want it to be closer to the center? Do you want it to be in the bulge where it has a lot of those close encounters? Or do you want it to be in a more stable part of the galaxy, out in the disk, away from a dangerous spiral arm, which could have lots of supernova explosions? Let's figure that out. Then what kind of star is it? Then all the stuff about the planet, what is it made of? How big is it? Where is it? How is it oriented towards its star? And then what's around it? So this is what I'm gonna do, but first I'm gonna give you your other options. If you don't wanna do just one planet, there's this really awesome book called Gideon the Ninth, which is set in a universe where there's one nation, I guess. They're ruled by an emperor, I think, but it's split across 9 different planets spread throughout the galaxy. So if you want to create a world where there are multiple planets, I would recommend not creating each planet from scratch, because that's a lot of work. I would draw some inspiration from real exoplanets. So this link will take you to the NASA Exoplanet Archive, which has all of the information we've ever figured out about the roughly 4,200 confirmed exoplanets. So you can go and you can pick out an exoplanet that's the right size and orbits the right type of star for whatever you want your scenario to be. If you're working with Earth or with an alternate Earth, then focus on the way that astronomy influences culture. You don't necessarily have to talk about biology if you're dealing with Earth and humans, but space does influence culture, and space is random, kind of. It looks random to us before we start to explore it and understand it. So there can be a lot of small changes that you make in astronomy. Like if the moon was just a little bit further away, we wouldn't have solar eclipses. So that would be a thing that's totally absent from folklore, which is a big way to influence culture. So think about that. So for the rest of class, we're going to be adding on layer after layer to one world, and we're going to do it together. So I will start in each class by building the foundation, and then I'm going to put in discussion questions in Google Classroom so that you can add on your own stuff. For example, once we get to the culture part of the class, maybe I will start talking about once we get to the folklore section of the class, I'll come up with some myths, but it's going to be a big world, right? I can't possibly come up with all of the myths that are going to be in this world. So I will ask you to think of other myths and other stories that might exist on this world. So together we'll build something that feels a lot more complete and rich. All right, so for this world, I've never built a world around an F-type star. And I just read a really interesting article about how F-type stars, because they are slightly less, K-type stars, because they're slightly less massive than the sun, they live for a lot longer. So they live for like 20 to 70 billion years, which gives life more time to form. So I'm going to put my world around a K-type star. It's mostly sun-like, it's a little bit cooler. So let's move the planet a little bit closer in. I don't want to deal with the difficulties that come with a gas planet. So I'm going to make it a rocky planet, but I'm going to make it slightly bigger than Earth so that it has weaker gravity. Yeah, I'm going to make it slightly bigger so it has weaker gravity. I haven't thought that through. Maybe it'll come back to bite me in the ass later, but you know, we're just going to deal with it. So K-type star, planet about 1.5 times the size of Earth, a little bit closer to the star, so it's the same temperature as what we have here on Earth. And let's say, okay, I'm going to ask you, what do you think the tilt of the planet should be? And I'm just going to take the first response in the chat. 45 degrees. All right. So the planet is tilted at 45 degrees. I will eventually write all this stuff down so that I remember it for next time. I'll also put this in Google Classroom. Where in the galaxy do we want this to be? I'm going to take another suggestion. Where in the galaxy? Towards the center. Okay, so towards the center of the galaxy, where you might have a higher chance of a close stellar encounter. You also have higher metals, so that's cool. I can imagine later on, if we have more metals, that might mean better things for technological advancement. That would be really fun. What other questions should we? Oh, what about other things in the stellar system? Are there other planets? Yes, okay, so there are other planets. How many other planets are there? 5, got it. Yeah, so every time I ask a question about the world decisions, I'm just going to take the first response in the chat. So 5 other planets, are they close together? Yes, they are close together. All right. So I think that's enough. We have a planet that's relatively close to the galactic center. It orbits a K-type star. It's pretty close to its star. It's about 1.5 times the size of Earth. It has a tilt of 45 degrees. There are 5 planets in this entire system, and they're all pretty close together. I think that's our planet. That's what we're going to build for the rest of the class. I know I went right up to time, but that's all I have. Oh, space is big. I covered that already. Next time we're going to talk about geology and climate. I'm super excited. We have our first guest lecturer. I'm going to let that be a surprise. But does anyone have any last minute questions before the end of class? What type of planet is Westeros on? Oh, that's a good question. Probably one that has a pretty unstable axis, right? If the lengths of seasons are always changing. But I don't remember seeing anything like when I was watching. You can see moons in the sky. I don't remember seeing multiple moons. So maybe it has really close planetary neighbors that are changing, that are making it wobble on its axis. Will I ever do an exolore on Earth, but if dinosaurs never went extinct? I will now. Yes. How do you estimate the number of rogue planets? It's through simulations, trying to estimate how many planets should form, and then based on interactions between different stars and interactions between different planets. Because remember I said planets migrate within a system. That migration can fling planets out of the system. So just through simulations, trying to figure out, like counting how many rogue planets there are. How do hot Jupiters exist? We don't know. Maybe they form close to their stars, but we don't totally know. So for other people, a hot Jupiter is a Jupiter-sized planet that orbits really close to its star. So a Jupiter-sized planet that orbits its star every 10 days. That's really fast. It's really close to its star. They might form there, but that's unlikely. We think that they probably form further out in the system and then migrate in. That migration can happen because of mostly gravitational interactions between surrounding planets. How big are the solid cores of gaseous giants versus a planet like Earth? I think it depends on how big the giant is, but I imagine I would not be surprised if the core of Jupiter was as big as Earth. Not Earth's core, but like Earth's wholeness. I don't know that for sure though, but it does just depend on how big and how massive a gas giant is. How did the elves in the Artemis Fowl series keep the ground from crushing them when the pressure is so high? I didn't read that series. Do they live underground? Is that what's happening? Yeah, probably magic. But if they live underground, then like the Earth itself has a lot of caverns underneath, like under the ground. So maybe they live in one of those caverns, and it's just being held up by basically the bonds between the rocks that make up the walls of that cavern. I'll read it. Yeah. All right, it's 9 o'clock. Thank you for your questions. I'm going to put some discussion questions in the Google Classroom after this, and I really am excited to see what you have to say on those questions.
Awesome. Thanks, Maya. And thank you everybody for joining us. Such a great course. I'm so excited. We've got, again, this is recorded. So as you saw from last week, we'll drop in the recording of this session to the classroom tomorrow. And then I'm also going to drop in that optional contact sheet into the classroom as well. So make sure to sign up for Classroom if you haven't already, and see you next week.
Bye, everyone. Thanks for your questions.